Yeah. Hi everyone. My name is Balaji. I am currently pursuing computer science in a specialization with artificial intelligence and machine learning in the College Institute of Aeronautical Engineering in the first semester. Today, as per my project on AAT Tech Talks, the subject matrices and calculus, mathematics, the topic of generalized Cayley-Hamilton theorem. Today we are discussing about the generation of Cayley-Hamilton theorem and applications of it and advantages of it. How do we derive it? How do we use in maths and calculuses? And what is the applications of Cayley-Hamilton theory in further future tech and also in the engineering career of the students? And diving into the concepts, let's start with classical Cayley-Hamilton theory. The classical Cayley-Hamilton theory tells us every square matrices A satisfies its own characteristics polynomial equation. What is the polynomial equation or the characteristic equation is A minus lambda I modulus of A minus lambda I is equal to 0. This is the characteristic polynomial equation of the square matrix A, which is given whatever may be the order. And here what happens is the square matrix A satisfies its own characteristic polynomial. That is, if P of lambda mod of lambda my A minus lambda I is equal to 0. That is P of A is equal to 0. That example, for A being a matrix called B and the 3 by 3, let it be a 3 by 3 matrix, and we are considering we are considering as the characteristic equation lambda is the characteristic root of the equation of the matrix, and we are taking the characteristic equation as mod of a minus lambda is equal to 0. Here whenever we state the polynomial equation there, we have to do the data and we have to get the characteristic equation. While solving that characteristic equation, the own matrix A should satisfy the equation. Whatever the value may be of the lambda, the equation should be satisfied. That means the equation should be equal to 0. Here, the motivation for generalization on the generalized Cayley-Hamilton theory. The topic name is on the generalized Cayley-Hamilton theory. What is classical Cayley-Hamilton theory? Generalized Cayley-Hamilton theory. Later, due to first of all, the classical Cayley-Hamilton theory was pronounced, and after that, for due to some consequences, then the theory has been generalized. That motivation for generalization theory was called by classical theorem applies to matrices over fields. Whatever the field may be, the whatever order may be the of the matrix, it classical theorem applies the matrices over fields. Generalization generalization needed for modules over commutative rings. It means generalization needed for modules over commutative rings. It may be across the field or within the field. It have to be generalized. It have to be applicable. It have to be scalable. It have to be modulable. So that useful in algebraic geometry, module theory, and ring theory, we have to its application is more useful and more scalable. That's why the generalized Hamilton theory was pronounced, and bridges linear algebra with abstract algebra. And here, if we go to the next slide, statement of generalized Cayley-Hamilton theorem. Let M be a finitely generated module over a commutative ring called A. Then let T is equal to M by 2M, that is matrix to matrix, be a linear map. Then T satisfies a monic polynomial with coefficients in A. This means T is integral over A. This is T integrated over A. Yes, algebraic interpretation. Here you may not understand. I will explain it clearly to you. The map T in the text end. The map T in the text end. It means here the text end means T is in the end of the line. A of M is a matrix. Behaves like a matrix. A of M is a matrix. The minimal polynomial of T lies in A of X. A of M is a matrix. But the elements or polynomial minimal polynomials in the matrix are A of X. Key inside is endomorphism of modules can be analyzed via polynomial identities. Here you can see the example over a ring. 1 minute. I can show you. Characteristics of polynomial is equal to lambda square minus 5 lambda minus 2. Then b square minus 5b is equal to 2y is equal to 0. Why did we get this? Means in the forward slide, oh sorry, it can't be done. And applications of generalized Cayley-Hamilton theory, not about the classical Cayley-Hamilton theory. Applications of generalized Cayley-Hamilton theory, we go module theory. As we discussed, it can be more applicable and more scalable. Module over rings. What is this module theory? Classifying module endomorphisms. Algebraic geometry. Studying shelf cohomology and morphisms. Endomorphism, cohomology and morphisms. Endomorphism and morphisms. Computational algebra. Symbolic manipulation of ring-based matrices and also control theory. Generalized system representations. And coming to the next, and we go here we go classical versus generalized Hamilton theory. Here you see the classical Cayley-Hamilton theory statement is every matrices A should satisfy its own characteristic equation. What is modulus of lambda minus A minus lambda into I is equal to 0 bar. And here you can see the P of A is a matrix, and the characteristic equation of the matrix is written as A power n plus A n minus 1 into A power n minus 1 plus and so on plus A1 into A plus A naught into In is equal to 0. But the generalized Cayley-Hamilton theory suspects that characteristic equation of matrices called P of A is 0, where A is an n by n square matrix, maybe the order of 3, order of 4, order of 5, anything. It is the characteristic equation is equal to 0. Here, left side matrix over field satisfies characteristics polynomial. Right side endomorphism over module satisfies monic polynomial over ring. Shows how theorem scales from linear algebra to abstraction algebra. And yes, coming to the next one, limitations and challenges of generalized Cayley-Hamilton theory. Limitations in general, according to my use, till now we have completed the module, second module in the max in our classes. And according to me, there was no limitations. We can use uh, we can choose Cayley-Hamilton theory for finding out the characteristic equations, characteristic roots, and after that we can also diagonalize the matrix and also find the orthogonal vectors and orthogonal set of vectors, orthonormal set of vectors, and also we can further proceed with the calculations in it. Till now, according to my prior experience, my own experience, I did not face any challenges or limitations in using Cayley-Hamilton theory. But everything, every theory or every maybe in example, you can take a classical physics there. Uh, it also has some limitations, some positives and some negatives. Everything contains some positives and some negatives. And here, coming to generalized Hamilton theory limitations and challenges, it requires module to be finitely generated. If you generate a module which is indefinite or it may be infinite, it can't take the input, it can't apply the method or something else on it. So that whenever you generate a module, it has to be finitely generated. It's have to be finite. The method has to be clear. The statement has to be done clear there. Now here, ring must be commutative. Only commutative rings are allowed in generalized Cayley-Hamilton theory. And also constructing the polynomial may be non-trivial. Trivial, non-trivial, and everyone knows trivial set of solutions or non-trivial set of solutions. Here, the construction of polynomial may be non-trivial. It only takes non-trivial set of solutions in the polynomial construction. And also interpretation depends on algebraic structure of A. What it means? Interpretation depends on algebraic structure of A. What is the algebraic structure of A? N by N. It is a matrix. A is a matrix. The algebraic structure of matrix is A. M into N. It is the order. Maybe 3 by 2 or 3 by 3, 4 by 3 or anything else. The interpretation depends. Whatever the interpretation the theory have to do depends on the structure of matrix. Depends on the given input to the matrix. And yes, coming to the proof of sketch conceptual overview, this is one conceptual overview. While Full proofs vary by context. The generalized theorem often relies on finitely generated modules M over a commutative ring A, as well as we discussed in the previous slide, and also representing the linear map T as matrix relative to a basis, constructing a monic polynomial f of x, or such as in the end of the text I have said, in the second slide I think so I have said that in the end of the text we use a of x is the format of coelements in the matrices such as dot f of t. There we used a of t is equal to a of x is equal to 0. Here we stated that f of t is equal to 0 using determinantial ideas or another normalization in advanced settings. This shows that T is an integral over A. A is a commutative ring. That is, module M is generated over a commutative ring, and also T is an integral for the commutative ring. That is, A is equal to A integrates to N into T. That's the main. Also, connections to other theorems. How Carey-Hamilton theory connect to other theorems, how it is applicable, how they divide the problem is minimal polynomial theorem. The minimal polynomial theorem divides the characteristic polynomials. From there on, Cayley-Hamilton theory take on the problem. And also Hilbert's basis theorem. I don't know exactly about the theorem. Still now we have not discussed this, but ensures finiteness conditions needed for module analysis. And Nigma's lemma, often used in module theoretics, proofs of Cayley-Hamilton. Module theoretics. We have M is a module and A is a commutative ring generated over M. We have seen this. And applications in algebraic geometry, it is we already discussed this. Endomorphism of conference sheaves satisfy similar polynomial identities, etc. Also, now I want to conclude with this short note. The generalized Cayley-Hamilton theory depends on our understanding of linear operations beyond matrices. It reveals how algebraic structures influence polynomial identities and integrity. And from matrices to modules, the Cayley-Hamilton theory remains a bridge between structure and symmetry. And wherever in the future, I hope it takes more easier way to solve the problems in the tech driven industry. Thank you for watching. Thank you, friends.